Okay, good afternoon. Please come in. This session is on Node.js does 30 billion transactions per day. My name is Joran Siu. I'm with IBM. A little bit about myself. I'm based out of the Software Development Lab in Toronto, so fellow Canadian. I'm the Runtimes Architect on IBM Z, responsible for our Java and Node.js runtime. In IBM, I guess in Canada, it's IBM Z. It's our premier enterprise computing platform. I spent the past dozen years working in the compilers technology area. Initially started off working on the Java space, so I worked on the Just-In-Time Compiler for IBM's Java runtime, which we actually open source as Eclipse OMR and Eclipse OpenJ9 right now in Java 1. Happening this week. So if you're interested in that, check it out, Eclipse OpenJ9. But a couple years ago, I got involved in the Node.js community. And it really came down to we had our enterprise customers wanting to do Node.js. It's one of the up-and-coming application platforms. And they wanted to do it on our IBM platform. So I ported V8 and Node.js to S390X. That's kind of the name for IBM Z. You see that in the Node community. And the picture on the right there is kind of what it feels like to be a compiler developer at times. I was running up Guardsman Pass in the mountains of Utah, 8,000 feet of elevation with an extra mile to go. And what I see there is, compiler work is technically challenging, but spiritually rewarding. The journey sites are spectacular. Once you get to the end, you get this great sense of accomplishments. But this particular talk is around 30 billion transactions per day. And it's really this proof of concept that we had done about a year and a half ago, mixing these four ingredients together. I have the fortunate opportunity to work on the IBM Z platform. It is a massive computing beast. On top of that, we put Linux. We support the main enterprise distros. We did our experimentation on Red Hat. We also support SUSE Linux and Ubuntu more recently. Now, as a kind of runtime engineer, I'm most interested in getting Node to perform and the Node stack to perform. So obviously, Node is a key piece there. We actually also use Mongo as the database, data store backend. And the application we looked at was AcmeAir. So for those of you who are not familiar with AcmeAir, it's probably one of the earlier Node benchmarks that were available. You can find the link on the bottom. It simulates an airline reservation system. It allows users to authenticate, log in, log out, be able to book flights, look up flights, track flight status. So it's really a simple application that mimics the real world. We liked it. I'd say it was the first application we looked at after we ported the entire Node.js platform onto our IBM systems. Previously, we were looking at more V8-centric benchmarks, pure JavaScript client-side type benchmarks. This was the first one we looked at. And it's also one of the benchmarks that's being tracked by the benchmark workgroup in the Node community. There are different flavors of AcmeAir. There's one based on Java. Obviously, I took the one based on Node. In the back end, it allows you to use a variety of data stores. The one I picked was MongoDB. Now, newer iterations of the AcmeAir benchmark, just wanted to mention, they have newer, there's a monolithic one, which the entire Node instance supports the entire application. But there's also a microservices version where it breaks it up into the specific tasks running in different Node instances. So there's an authentication server, flight status type service and whatnot. In this particular example, I decided to focus on the monolithic one. Now, I want to talk a little bit about the hardware platform that we run on. How many of you have heard of IBM Z or Linux 1? A couple people. So this is our premier enterprise computing platform. A lot of our biggest customers, major companies across many industries, rely on this computing platform for the most mission-critical data as well as transactions. It's really an I/O beast. It supports, unmatched scalability. And I'm an engineer. I can't market this, and I don't expect anyone to really go off and buy a Linux One system. But just to give you a sense of the scalability, we're able to run a MongoDB database, a single instance, to support 17 terabytes of data, and still match in terms of the read-write response times in under 10 milliseconds, right? And this is the type of system where it scales up in a single instance. It's just the I/O bandwidth is just that impressive. But it also scales horizontally. We're able to put 2 million Docker containers in a single box, and have all of them perform. Continuous business availability. I think that is the reason we named IBM Z. Z for zero downtime. It supports 99.999. There are 5 nines in there. In terms of uptime, and there's actually a metric there. You go online and check, right? I think it counts to like literally seconds of downtime in a given year. There's a lot of redundancy built into this system. A core would potentially fail, and the workload will automatically get migrated onto a spare processor. If the entire mainframe has issues, companies set up disaster recovery sites. Things get offloaded literally in seconds. And finally, security. Everyone cares about security nowadays, especially on a computing platform where you're putting some of your key assets and data. I'll say 2 things on that front. We have crypto cards that stores private keys. Those things, you don't want anyone else to know your private keys. They're actually tamper resistant. So if it detects that someone is trying to physically inspect it or tamper with it, automatically wipes out your keys so they can't access it. The IBM blockchain solutions, our premier solution that is available on our Bluemix platform. There's only one platform that we trust to run the hyperledgers and the smart contracts, and that's on the Linux One system. So fortunately, I work at IBM. I have access to one of those systems. I think this is an interesting picture. Back in 2011, we know there was a big earthquake in Japan. Tragically, their nuclear reactor had issues, right? And so I contacted some of the folks that I know at the Tokyo Research Lab and asked them, like, hey, are you guys okay? Fortunately, they were fine. They sent us this picture back saying that this was our mainframes. This is like seeing Lamborghini on the side of the road, like, wrecked, right? Like, this is not a pretty picture to look at. But apparently, these mainframes are still up and running, even though they're on the side. And check out that YouTube link. It's actually like a 2-minute video, but these systems are actually earthquake tested. You actually see the frame like bend out of shape, right? But they actually test this, and I don't know any other computing platform. I guess NASA will probably do that type of stress testing on their systems, but quite resilient. But perhaps the coolest thing I find, especially in this community, is with our friends at Marist College, we were able to provision, and Marist College, they run the Linux One community cloud. So if you want to get access to one of these systems, just go to the community cloud. You can provision an image for free for 90 days or 120 days. But we were able to provision a couple of these systems and integrate it in Node CI. And consistently, in terms of build and running the tests, Linux One runs it the fastest. To the extent that community have spoken and said maybe we should use Linux One as the platform to run the test first, right, to detect issues before consuming resources on the other platforms. But getting on topic, AcmeAir. On the runtime side, we took this as a Node application. We want to understand its behavior. So we ran it on Linux One. We ran it on kind of the latest Intel server that we had. Out of the box, it was just 2.5x better. I put 2 generations of Linux One. We actually recently announced Emperor 2 a couple weeks ago. We saw a nice 20% jump in terms of performance from that, which is really cool. I'm happy with positive numbers. But it was a little bit odd at times too, because when we were developing V8, we were looking at Octane, JavaScript performance, right? So this is like how well can we optimize the code within the JavaScript engine itself. I would say when we first did it, we were behind. Partly, kudos to the V8 community and Google engineers. It generates actually really nice Intel code. We spent a bit of time, implementing kind of hardware-specific opportunities, optimizations. We redid the same thing again when we moved to ignition and turbofan. But in this case here, AcmeAir out of the box was 2x better. And the engineer in me was like, I need to understand this. 2x is cool. But with Octane, we're plus or minus 20% range, not 2x. So what's going on? We ended up collecting all sorts of profiling data, and this is if there's one thing we recommend, and you see this in many sessions here at Node Interactive. This is about you need to monitor your application, profile your application, understand the hotspots, understand where time is being spent. And in terms of AcmeAir, the amount of time spent in Node runtime itself is relatively small. And this, we actually isolated MongoDB away, right? So this is like MongoDB running on the same server, and I have Node running either on Linux 1 or on our Intel Linux, connecting to the same MongoDB, made sure network is not a bottleneck. And yet, despite Node being a relatively small part of the overall CPU consumption, we're still seeing the 2x better performance. I'm going to take a look at here. The V8 optimized code, so this is where looking at V8-centric benchmarks, we were really making a lot of improvements in. Was less than half of the Node runtime itself. Garbage collection was an aspect of the Node binary. But even if I were to take away, improve these things, I'm not going to get 2x better performance, right? So what we dug a little bit deeper, looked at different types of reports, SAR reports or whatnot, and we found out that it was actually the I/O performance that was key here. And this is where I think the Linux 1 platform really shines. We actually have 320 power processors. So you're buying an IBM Linux 1 system. There are 141 cores, and we'll kind of get more into that later as the experimentation, but we actually have 320 power processors built into the platform to accelerate I/O, and there's both file I/O and to accelerate network I/O. So running libuv tests, for example, there's a benchmark within libuv. We're seeing similar, double the performance that we're seeing. So it's not so much the Node runtime itself, but it's really the underlying operating system and hardware support that really accelerates this. And it kind of makes sense because Linux 1 has always been our data serving and transaction serving platform. We really want, it's been finely tuned and optimized for this type of workload, which really matches well with Node.js type operations. So getting into the actual experiment, we wanted to, we know that Node itself runs well on the platform, but what if we took the entire box with all 141 processors? And can we get this thing to scale? And this is the challenge. So we really started from bottom up. We wanted to make sure that if we had the full power of the machine, we come up with a methodology that allows the entire workload to scale. So in this case here, I'm just going to briefly touch upon the hardware topology of how this works. So here, in each one of the boxes represents a chip. There's 8 cores on the chip. You see they're actually clocked at 5 gigahertz, so relatively high frequency, which is really great for single-threaded performance. But then there's 6 of them, so you get 48 processors connecting to the same L4. And you'll see here, the cache sizes on the right, they're actually quite generous. You're talking about almost 1 gig of cache in L4. And then each of the dotted boxes is replicated 4 times. So there's actually what we call a drawer. It's literally physical drawers. Like you imagine, the Linux 1 system, it's like a double door fridge. You open up the French doors, and then you actually pull out 4 drawers, each one consisting of 48 general CPs. So understanding that and understanding kind of the Newman effects of having to communicate from one core across the memory fabric to access memory on another drawer is going to be expensive. That's kind of one of the areas that we started off with. But before I get to that, the initial topology. So we have the system under test on the right. We have a Linux 1 system. We have node instances. We expect we need to scale horizontally, similar to microservices in the sense that like if one instance is saturated, it's not meeting the response time targets, we need to bring online more instances. We also have MongoDB instances. But on the left, we have a load balancer. In this case here, we chose HA proxy. No particular reason, we just wanted a fair load balancer. It essentially distributed work round robin style. We made sure that for a particular session, it gets sent back to the same node instance. And then we have JMeter. JMeter is really the workload client driver. We want to push, this is what simulates the REST API or the API calls into Node to log on, buy flights, and whatnot. In terms of tuning, so this is where the fun comes down. We want to find the optimal configuration of Node and Mongo ratio, right? And this is where you need to look at the SLAs and make sure that the response times are satisfactory. As you scale one up, does it have an overall improvement, or at some point you get diminishing returns? Starting from a system level, I kind of mentioned the drawer configuration. We make sure that we don't go cross drawers in terms of communication when where appropriate. So we actually decided we have 4 drawers. We're just going to put 4 instances, and we call them logical partitions on the system. So we literally have 4 separate Linux guests running. Each one is laid out to the specific processors on the core. Looking at I/O, we need to make sure that network I/O, for example, is not our bottleneck. So we made sure that we had the network interface cards supporting 10 gigabit networks available for each one of the 4 Linux guests. File subsystem, we made sure that we had the fastest disk available. Even setting up the network itself, from the HA proxy and the client driver, we want to make sure that they're, we set up private subnets so that they for sure won't be a bottleneck. On the Linux side, the standard Linux tuning for Mongo, we made sure that we enabled large pages, adjust the number of file descriptors and other parameters. I think one interesting thing, that's common, especially for performance tuning. If you're native on a system, is pinning. So we thought, Node, and even from profiles, is dominated by a single-threaded, is our single-threaded event loop. There's that common misconception that Node itself is single-threaded because of that. And when you actually pinned to a single logical processor, you actually get worse performance. And that comes down to kind of the libuv or asynchronous library itself is actually a multi-threaded application. I think by default it takes 4 threads, right? Even V8 itself is a multi-threaded application. So pinning to a single processor core is even though it's dominated by 1 thread, it's not necessarily optimal in terms of performance. As you can imagine, we scaled large number of Node instances in the entire box. We definitely use Docker. We actually measured that as well in terms of what is the overhead of Docker, because we want to squeeze as much performance out as possible. So with AcmeAir, we measured the overhead to be around 2 to 3%, which is negligible in our case. So we're okay, for all the benefits that you get in terms of containerizing your application, 2 to 3% is something that we're willing to give up. AcmeAir, so this is the application level tuning. Fortunately, AcmeAir is fairly lightweight. I mean, we didn't spend too much time in AcmeAir. But this is where you want to look at the flame graphs. You want to see where time is being spent within your application. One thing that jumped out at us, and if anything out of this entire list, logging was probably the biggest performance factor, right? And by default, they just generated, logged out a lot of information. depends if you need it or not. Sometimes, in your real application, you might need all this logging data, right? They might feed into, performance metrics, right? Or, recovery type modules and whatnot. In our case, we decided that this was such a big overhead. We switched it to warn, so only for warning messages. So when something goes wrong, we have that recorded. Similarly, on the load balancer side, you have to do the typical tuning, make sure that the appropriate network channels are available, the timeout settings are reasonable, and whatnot. So a lot of work and a lot of experimentation around this. What we ended up configuring, and you'll see here, there's this image multiplied a little bit, a single Linux blade, which has 24 cores actually. It wasn't sufficient to actually drive the full Linux 1 system. We ended up multiplying that by 4, multiplying the load balancers by 4, actually splitting the load balancers up because that became a bottleneck. The ratio that we found most optimal for this application was 15 node instances for 1 Mongo. Then that gets sharded kind of in the back end. We kept Docker in there. That was the 2 to 3% instance, and we just kind of replicated that. I think the beauty of Node and this topology, and which is, I'd say, a little bit unique because we look at other benchmarks, we look at other workloads in different languages and platforms. As you scale to 141 cores, they don't scale linearly. At some point, you start hitting at a resource bottlenecks or whatnot. With Node, it was actually relatively lightweight, and even going back to my previous chart. Even here, as we scale the number of cores, you see, it's fairly linear. And we were actually quite surprised as we, took one drawer system, one image, and scaled it out to all 4 drawers that it was actually fairly linear. So our final result, we have 15 instances of Node in Mongo. We want 2 sets of that per drawer. The number of cores vary. You see like 141 cores actually isn't even. It doesn't divide by 4 nicely. So you have 34 to 36 cores. There's actually 48 cores available, but underneath the covers, the spare cores that I mentioned in case one of them fails. So we keep a bunch extra. Make sure there's enough memory, Ethernet. The average throughput per drawer was just under 90K. We managed, once we got the full 4-drawer system set up, to achieve a transaction of 360K, which translates to over 31 billion transactions per day. I think through the process, the short message I can give is definitely, if your Node application is relatively lightweight, but it's this is the classic orchestration type use case for Node, right? But I'm making a lot of calls to different services to backends. You definitely want to pick a platform that has high I/O bandwidth, but make sure to profile your application. See where time is being spent. Monitor your application. So I'll finish off, with some links. If you're interested in Linux 1, so this is the same box really that we have the Node community images on. You can go to that link, give it a try. The AcmeAir benchmark is there. It's easy to set up. You just clone, bring up Mongo, point to it, and you're pretty much up and running. So thank you so much.